Okay. All right. I think we're live now. I didn't see the record thing pop up, but I'm guessing it's working. Okay. So welcome back. Hopefully you guys had a good 4th of July. I enjoyed myself. I didn't get as much done yesterday as I had intended to, but I'll get caught up on it today and tomorrow, and we'll get things together. The last time I know we had a technical difficulty. I tried to reproduce the problem on the board that we were working on. I had to erase it because I had to use the board space for another class, but I put the pertinent information on there. I think we need to finish the problem. So if this is your first time for this lecture, you want to go back and look at the previous lecture. You'll see that the end of it got cut off. I think we had an issue with the camera. So I'm going to try to pick up where I left off. I have most of the stuff here, but some of the quantities, I don't have everything up here. Like I left this blank because I got the totals here. But we ended up with this triangle. That's the most important part. So what I want to do today is I want to finish this problem. This is the last of our power lectures. We did two, three. This will be a total of 3 power lectures. The title of this is called Power Factor Correction. So we'll finish that. And after we're done with this, I want to talk about another topic. I put a video out there. I didn't really give you a lot of time. I think I did it a couple hours ago, but hopefully you got a chance to watch the video. If you didn't, we're going to talk about the video. If you didn't watch it, it won't make sense what we're talking about, but you can go back and watch it later, and then hopefully what we talk about will make sense.
Was the video?
So today I'm excited. Go ahead.
I'm sorry. Was
What
the
did you say,
video
Dominic?
was the video not supposed to have sound? I couldn't hear. I couldn't hear anything on it.
Yeah. Yeah, so there was 2 versions. There's one with sound and that one without sound. But the one with sound is just classical music. So I mean, there's nobody talking, but there's either you listen to that or you listen to
Okay.
classical music. So, but we'll talk about that. I'm excited because this is my favorite topic. I mean, there's a lot of stuff in AC that I think AC kind of pulls together a lot of things. But this is my favorite topic. Of all the things we talk about, I think I enjoy what we're going to talk about today, probably today and next time we get together. And there's a lot to this. I think you'll be very pleased. This answers a lot of questions that you might have wondered and thought about. So we'll talk about, it's called resonance. We'll talk about that today. So before we get into that though, let's we just kind of back up and go back to, let me see if I got the problem statement. So we had this problem. I like this problem because we talked about modeling. You can model a whole factory. You can model a whole city. You can even model a whole country as an electrical circuit. So here's an example. It says an industrial client is charged a penalty if the plant power factor drops below 0.85. We talked a little bit about power factor, but today you'll see why having a high power factor is desirable. Matter of fact, the math will show you some things that you can take away and help you understand to clarify some things. So this is a factory, and on the factory, I think this was 12 kilowatts. So there's no one light bulb that's 12 kilowatts. That's silly. But all the light bulbs together in the factory, the total power dissipation can be 12 kilowatts. I forget what is this thing here. It says electric furnace. So electric furnace has probably resistive elements that heat up. And then it has a motor like a blower. We have a reactive element to it, so we can model that as a wire resistance, R sub W, and then the reactive component. Then there's some kind of motor, and for the motor they did something interesting. For the motor, they told us it was I don't have it on here, but it's an 80 kilowatt motor. It's an 80 kilowatt motor. But remember, a motor basically is fixed magnets and the coil. So they can tell us it's 80 kilowatts, but the fact that it contains a coil, even though that coil is not an inductor, coils have inductance, so you can model the coil as an inductor. Now they didn't do that here, but my point is we know we got resistive watts here, right? We got watts, but since there's a coil and every motor has a coil, since there's a coil in here, basically we got an inductor. We have an inductor. How do we figure out the reactive power here? Well, you learn something that what you can easily find for a motor is the power factor. They gave us a power factor for the motor of 0.8. And since we know the power output of the motor was, or the power of the motor was 80 kilowatts and the power factor, we were actually able to draw a power triangle just for the motor, not a system power triangle, a power triangle just for the motor to solve for the reactive power of the motor. And we were able to fill this trial over here, and we ended up with 146 total watts, 146 kilowatts, and 132 kilovar. So if you did not attend the last lecture, then please go back and watch the video to fill in the steps here, because we're going to kind of pick up where we left off. But again, this is it's a simple circuit, but there could be thousands of light bulbs. There could be several of these things. You can model big systems as a simple circuit like that. So the power of DC circuit analysis and the power of AC circuit analysis in general, you don't just have to work on these itty bitty circuits on the board. Anything that can be combined and represented pictorially like this, you can start combining stuff and actually represent large electrical systems as a simple circuit that you know how to analyze. Hence the reason, guys, you'll make the money that you make when you get out of here, we hope. Because everybody can't do this, so they can do it, they don't want to spend the time learning how. But anyway, we have an industrial client. They're charged a penalty if the plant power factor drops below 0.85. The equivalent plant loads are shown in the circuit here, and they give you a frequency. So we know that the generator for this factory is 600 volts, and we have a frequency of 60 hertz. They want us to find the total power and the total reactive power, so the watts and the bars, and we did that. We went through, we got 146, 132, and from that we were able to determine this power triangle. Now this is the power triangle for the whole system. We're able to determine the power triangle from the legs of the triangle. We were able to get the total apparent power is what that's called, and then we were able to take our power factor, which was, what was it? I think the power factor was, I can't remember. Was it 0.8 or something? Somehow we came up with this angle. I can't remember if they gave us a power factor. We did an inverse something, but that's on the other video. But here's what we want to do. How do you increase the power factor? How do you increase it? Why would you want to increase it? Well, that goes back to what I was trying to explain to you before. Look at the power factor. We know the power factor is between 1 and 0. And the way you get that power factor, the way you get that number, is by taking the cosine of theta. And the only way that that can be a 1 is if that angle is 0 degrees. And the only way that that can be a 0 is if this angle between the current and the voltage is 90 degrees. You know from your trig, the cosine of 0 is 1, and the cosine of 90 is 0. Well, if this angle is between the total current and the total voltage. When is the angle between the total current and total voltage 0? It's only that way when you have purely resistive loads. The voltage across the resistor is in phase with the current through it. This is the phase angle between those two quantities. And it's a 0 when you have a resistive load. When is it 90? When you have reactive loads. Now, I mentioned a long time ago that resistive power is the only kind of power that can do work, because to do work, you got to convert power from one thing to another, from electrical energy to heat, from something to something else. Reactive power is not converted. Reactive power is stored and returned to the system. It can't do any work. So it's highly inefficient when you have bars in here. You want to get the bars out if you can. So how do you do that? Well, what we do, if you think about it, like this. Something just popped in my head. If you think about this, think about the impedance diagram. Now you all know the impedance diagram like this. And this is R, this right here is XL, and this is XC. Well, they don't really, I'm making this up right now. So this is an impedance diagram. I'm going to change it to a power diagram. There's no such thing. What I want to show you is, if I multiply this by I squared and multiply this by I squared, if I multiply everything by I squared in this diagram, just like an equation, I don't really change the relationships between the quantities. But what I do change is opposition times the square of current now is power, becomes power. So what I have now on this axis right here is basically QL. Those are inductive R's. And down here, I have QC. Those are, again, inductive or capacitive R's. And right here, I have power. So given 132, now I forgot to put this a positive 132. You see we got inductors here, we got inductors in the motor. So how do I take positive R's? If I want to get rid of some of the positive R's, how do I get rid of it? Well, if you think about it, if I want to go down this way on the diagram, what I got to do is add some of these negative R's to it. So I can use capacitive R's to cancel out inductive R's, and I can use inductive R's to cancel out capacitive R's. I don't know who figured this out, but whoever did it was a genius, because you can actually add capacitance to the circuit to increase our power factor, which overall, as you're going to see at the end of this, is going to make our circuit way more efficient. And so how do you do that? Now, I think Jacob and Dominic, I talked to Jacob. I talked to Jacob, I think when the camera went out. And, oh no, he sent me a text. Jacob sent me a text, and they came up. I think him and Dominic went through this, and they figured it out. And so Jacob wanted to know if his number was okay, and that he came up with for the total capacitance that you add in parallel with the circuit. You can add it anywhere in parallel. And the value that they came up with was correct. So Jacob, I never got a chance to text you back, or Dominic, but you guys figured it out correctly. So I think Jacob sent me a text, I want to say Thursday or something, and asked about the number that they had gotten. So I'm impressed that they actually took the time to go through and figure it out without me walking you. They just kind of went through the steps. So that's beautiful. That's beautiful. So you guys applied yourself and you came up with the right answer. But let's go through it together. And what I was talking about last time was, here is the power triangle that represents the system as it is right now. Now what we want is, we want to raise the power factor. Let me put my other diagram back up here. We want to raise the power factor. Now, you got to remember, raising the power factor decreases this angle right here. It's kind of counterintuitive. So what I'm saying is, if you remember, you get a power factor of 1 when the angle here is 0 degrees. You get a power factor of 0 when the angle between the voltage and the current is 90 degrees. So they're referring to the angle between the voltage and the current, or that power factor. You take the inverse of the power factor, you get the angle between the voltage and the current. So this angle in here, that inverse of the power factor, tells us the higher the angle, the closer it is to 90, the closer that angle is to 90, the closer we are to 0 over here. The closer the angle, this angle right here, the closer that is to 0, the more I can bring that side down to get this angle smaller. If that angle is moving up, the power factor is going to be closer to 1. In a perfect world, I would make it 1, but God won't let us do that. We can't get all the way to 1, but we can get close. We can really increase it a lot and save us some money. So how do I lower this angle? Well, you can't adjust the resistance. Resistive watts. You can't take resistance out of a circuit without physically changing the nature of the circuit. I mean, some of the resistance is in the coil of the wire. You have to shorten the wire. You can't do that. But what you can do is, you can work on this side of the triangle. So I can't really work on this side, nor would I want to. But if I can decrease this side, which represents our inductive bars, if I can decrease that, then I can lower that angle down, which is going to take me closer to a power factor of 1. I think 0.85 was the limit. So the question you want to ask is, okay, according to the problem statement, we want to bring the power factor up. I think it was 0.8. We want to bring it up to, it might have been 0.79, but whatever it was, we want to bring it up to 0.85. So bringing it up to 0.85, now they speak in terms of power factor, but you want to think in terms of an angle. So you ask yourself, okay, I want to bring the power factor up to 0.85. What angle is associated with this? And so what we figured out was, all right, we're going to take the inverse cosine of the power factor to get the associated angle. And somebody, I think it was Jacob, told me it was 31.8 degrees. Okay. That means you want to lower this side down so that this angle on this side now is about 32 degrees. So I think when the camera went out last time, by the way, I had a class this morning and it did the same thing. I was on the camera for maybe about 2 hours. I don't know if it overheats or what, but hopefully it won't overheat while I'm in the middle of my favorite lecture. I'll be pissed off to the highest of festivity if it goes out when I'm talking about resonance. But we'll see. So anyway, 32 degrees. I want to lower it down. By doing that, though, look at what happens. I want to actually bring the angle down so that the side over here, right there, I want to bring the angle down so that this angle right here is 31.8 degrees, about 32 degrees. And by doing that, my power factor will go up to 0.85. So the question is, how do you do that? Well, you see, the answer is right here. I have 132 kVAR. And what I want to do is this piece right here, I want to take it down. I want to get rid of this right here. So I got to add some Q. So I'll call that Q added. You probably can't see it in the camera. That says Q, and that's subscripted with the word added. So if I add some negative bars, I can reduce this 132 down to whatever this is right here. This is what I want right here. So I'm going to call that Q new. I'm going to call that Q new. Now, you can't, oh, there it is. Hold on, I lost my cap to my camera. All right, so what I wanted to do last time, and this is where the camera went out. You see I got a triangle in here. That's the new triangle I want, that little triangle. So let me pull that out over here so you can see what I'm saying. You can see it more clearly. So if I draw that little triangle over here, let me see. I guess I'll keep the black marker. All right, so I'm gonna pull the little one off, and here's what it looks like. Now notice we're not changing that leg. The resistive leg is still 146. This side right here, that's what we want. We want to add some negative bars to push that side down so that right here, this is what I'm calling Q new. And I know by taking the inverse of the power factor that they gave us, the one that they want us to get it up to, I know that this angle right here is about 32 degrees. So you can see this right here now is 31.8 degrees. So we know the angle on the side. If we know an angle on the side with a right triangle, you can solve it. If you know two sides, you can solve the right triangle. If you know an angle on the side, you can solve a right triangle. So we've got an angle and a side, we can solve this. Now, the tangent pops up a lot in electronics because usually the opposite side and the adjacent side, you're dealing with, those are the unknowns. Usually you're dealing with, something that's unknown on one of those legs. So it's always that. So the inverse tangent keeps popping up. But the point is, if you know your trig functions, you know that the tangent of an angle in a right triangle is equal to the opposite side over the adjacent side. So that's what they taught you about the tangent. And so all we got to do is we got to name it. I'm dropping everything today. So we'll name this. Well, the opposite side, you see we're calling that's Q new. So this is Q new. That's like our unknown. Our adjacent side, that's the 146. And I want to just write 146 because we know it's going to be in K. So we'll just write 146. That's 146. So we know that number and we know this number. The left side is the tangent of an angle. And we got the angle is 132, 131.8. So we got that number. tangent. No, I said it's 31.8. I think I said 130 something. But anyway, just a little bit of math, you can solve it. It's pretty simple. So I multiply both sides by 146, and I get Q new equals 146 times the tangent of 31.8 degrees. Now, I don't have a calculator. I don't know if I told you guys, I lost the calculator I've had for years. I can't find it anywhere. So I'm going to need somebody to calculate that. Make sure you're in degrees and not radians. Well, give me 146 times tangent of 31.8. Let me know what that is.
It's 90.5.
All right. Now, that's golden. That's beautiful, because what you just did is you told me you said 90.5? 90.5 kVAR. So I know this side right here, look at this. I know this side right here, that's 90.5 kVAR. And I know the total is 132. So if I take the total, the 132, minus that piece, the 90.5, that leaves me the piece that I want. Beautiful. I mean, this is gorgeous. So I'll get rid of this. Q, I call that Q added. That's how much Q I got to add to it to bring that side down to what we want. So Q added is just I'll just call it QT. QT minus Q new. So QT is this. That's our 132 minus Q new, we said was 90.5, and this is in K. I'm leaving the units off because I'm out of room. But on your calculator, take 132 minus 90.5. Let me know what that is. (32 minus 90.5).
41.5.
Let me turn. I got a fan over here because you guys don't know I got lights to get this camera to work right, and it is hot as hell down here. I got a fan. I'm gonna turn it up a little bit. Hopefully it doesn't get picked up by the microphone. I have a choice. I can either burn to death and leave my fan down low, or I can turn it up on high and choke to death from the dust in my basement. I don't know. So understand what this is. It's 41.5. That's the number of negative bars we got to add to push these positive bars from 132 down to 90.5. And where do I get negative bars? I get negative bars by adding capacitors to the circuit, a big capacitor. So I know that this, now it doesn't say it implicitly, but you got to know that 40, that's negative, meaning I gotta use a capacitor for that. The way you cancel out inductive bars is by adding capacitive bars. The way you cancel out capacitive bars is by adding inductive bars. And I tried to show you that with that little power triangle thing that I did a little while ago. So here's what we know. We know that in order to get this to work, I gotta add a capacitor in parallel with everything in here. And that right there, I'm going to have some negative bars. So I'm going to add some QC there. And I know that QC is going to equal 41.5 kVAR. The question is, what size capacitor do I make it? How many microfarads is that? Well, to get that, what I got to do is, I got to do a couple things. They gave me the frequency there, so they didn't just put it there to be cute. They want me to use it. So if you think back, now this has been a couple weeks since we did that, but I got to some kind of way get from bars to microfarads. And I can tell you right now, there's no direct link that I know that'll take you from bars to microfarad. but I can do it in 2 steps. I can go from vars to opposition, and then from opposition to microfarads if you remember your equations. So let's do it. Here's what I'm saying. I know that Watt's law, one form of Watt's law says that power, QC, is equal to the voltage squared over the opposition, XC. I know this. We just figured that out. That's 41.5. I know this because they gave it to me. That's the system power. The only thing I don't know is XC. I can solve this for XC, and then if you remember what XC really is, once I get XC, then I know that XC is 1 over 2 pi FC. Well, if I solve this for XC, I got that value. And the only 2 unknowns here would be the frequency and the capacitance. And they told me the frequency is 60. So the only unknown here is C. So by going from power to opposition, we're able to go to find the capacitive, the size capacitor I need to add in parallel with that circuit to bring the power factor up. So let's do it. Now I'm impressed that, because I mean, it's not particularly hard, but there's some steps and thinking, mathematical thinking you got to do. So I know Jacob and Dominique worked on this and they came up with the right answer. That's impressive to me because I've only had one other person do that. It's an African student that had in the year before last. And he was the only one able to work through this without just thinking about it a little bit. So I don't know if anybody else worked on it. I only talked to Jacob, but if you did, and you got this, that's impressive. You're thinking the right way. Let's put the numbers in here and let's solve this. We know this is 600. I'm going to leave the units off. We know we want this to be 41.5. We don't include the negative sign here. So we want 41.5. You know what I'm going to do? You guys are probably smarter than me, but I'm going to write this out. I'm going to write this as 41.5 times 10 to the third. And that was 600 squared over my unknown here is XC. So I didn't know what that was going to be in if I left that as in K. So let's go ahead and solve this now. XC is going to equal 600 squared divided by 41.5 times 10 to the third. I'm leaving the units off, but you guys should write it. All through school in physics and engineering when I was coming up, they just grilled us on units. I feel guilty when I don't write them, but I'm out of room. So you got to write them. Okay, so 600 squared divided by 41.5 times 10 to the third. Somebody tell me what that is. Oh.
8.67 ohms.
All right. So we need 8.67 ohms. So the question is, what is that if I convert that to farads? And so all I got to use is use that last equation, and we're good to go. This is another reason why I have you guys. I get some complaints that I don't let people use equation sheets. I want you guys to know the equations. Now we're kind of at a disadvantage this summer with the shortened time, but I would have you write these equations over and over and over again until you just can see them in your sleep. But you got to know something exists in order to use it. If you got to look it up, there's too many equations in AC for that. You got to know some of this stuff. So you got to know that. Man, this looks so beautiful. I hate to erase it. It just looks technical, doesn't it? I mean, all these colors and anyway. I guess I'll erase this. So I know that let me just put it up here like this for right now. So we got XC is 1 over 2 pi FC. And then if I want to switch these, I got C equals 1 over 2 times pi F is 60 times 60, and then this value right here, XC, you're going to stick that right there. So on your calculator, somebody, you don't have to do the division thing. You can use your reciprocal key. Just do 2 times pi times 60 times 8.67 equal, and then hit your reciprocal key and let me know what you get. That's the answer we're looking for. Let me see who's out there taking a long time. Dominique, Sam. Sam's out there. Jacob, Tresser. Are you there, Tresser? Or did you just turn it on there and walk away from the screen so I think you're there? You see, guys, see how you can just, without you opening up your cameras, I don't know if you're really there or not. So I see Tresser's image there, but he's not responding. So when you guys don't calculate for me, I can tell if you're there or not. I think Jacob's the only one out there.
I don't want to just read everything off of my paper. I already did it.
Yeah, I'm
here.
He said he's here. He's just got mic issues.
If you don't read it, and the other two are not going to participate, and Pressure's going to have mic issues, I'm stuck. I don't have a calculator. We're going to be here all night. I want to get to resonance.
All right, I got 3.06 times 10 to the negative fourth. And then when I switched that over, right? I got 306 microfarads.
That would be correct. That's correct. So I like this problem because it brings in a lot of stuff. You got to know your AC. You got to, just the modeling aspect of it. You got to know your trig. I mean, this is a good problem. I mean, it really, really is. So it's here. It's on the video, guys. Study this. Now, if we were on campus actually having exams, this is the one that would give people a little trouble because you wouldn't be able to use your notes. You got to know the steps. But see, the fact that a couple of you already reasoned through this and got the right answer, you'd be surprised when you push yourself what you can learn. But this is a very, very good problem. And it's a practical problem. To you, you can say, okay, I see how you got that. But the average person has no idea what you're doing. So if you actually did this, they could hire you as a consultant to go in and say, all right, if you model a factory like this, and you as an engineering consultant, what do you need to do to bring my power factor up? I'm getting a really high electric bill. The Duke Energy keeps penalizing us. What do I need to do? Well, you got to do power factor correction. And to do that, you don't have to do it. You're not installing it. You got to tell them what to do. So as a consultant, you would go through these calculations that we did on the board here, and you come up with a value. You hand them a piece of paper with these values on it and say, here's what you got to do. Now give me my $10,000. And I'm serious. I'm not laughing right now. So you're going through this. You're learning how to do stuff like this. This is something you can apply directly. There's people called energy consultant. This isn't all they do, but this is some of the stuff that you can do when you go through and you understand AC power. So this is a good problem. Very, very, very applicable. Now we're not done yet though. This is only part. This is probably the hardest part right here. I shouldn't say hard. It's the most involved part. Because it says what capacitive value in microfarads is required to bring the power factor up to 0.8 was 306 microfarads. But the last part, it says they want the generator current before and after power factor correction. Now, the point of this is to show you how we improve things with power factor correction. If you increase the power factor, you increase the efficiency of the system, and that results in big savings. Now, the way that's done is there's going to be a reduction in current, but you can prove that by going through the math for this last step. So the last step, if you, I don't know if you guys calculated this part or not, but if not, just take out a piece of paper, and they want the generator current before and after power factor correction. So how are we going to do that? Before and after power factor correction. Well, I'll tell you right now, anytime you're dealing with AC power, just start with the power triangle. Just work off the power triangle. So some kind of way, you may not know what to do, but you know you got to start with the power triangle. So I'm going to let's draw the power triangle before power factor correction and after power factor correction. Let's do that, and then we'll see if we can use that to help us to solve it. So we need the before and the after. All right, so here is before. Now this we kind of already got, right? Because this right here. We got 146 base. We got 132. 196.8. So this is before. After power factor correction, what we have, we still got 146 here, but we reduced that down to, I think it was 90.5. Now we got to get this new side right here. So somebody give me this side of our new triangle. And this is the right triangle.
It's 171.8 kVA.
Okay, so what you know, in a perfect world, what I would be able to do is, if I can make this side right here go to 0, that means the hypotenuse of the triangle and that resistive side would be equal to each other, and I have all watts. And all those watts can do work if I had it in a perfect world. Here you can see I've reduced it, so the hypotenuse has gotten closer in size to the base, the resistive power, because that angle's smaller. But let's figure out the current in this with this triangle. What would be my current in the circuit? Well, I'm not going to deal with any angles. I mean, let me show you what. I hate to erase it. I got to erase it at some point. I might as well get used to it. It just looks so technical and beautiful. I just love it. People, when I was in college, I'd do stuff like this with all the colors, and girls would just think you were so smart. I don't know why.
I know my wife kind of rolls her eyes at me when I'm doing this.
All right, so remember that the correct equation, I'm not going to use the correct equation. Remember from DC, P equals V times I? Well, in AC, we treat them in all its phasors. We go S equals V times I, but that's I star. And remember, that's the complex conjugate. But the thing is, I haven't given you any angles. We haven't talked about the angle, so I'm not going to worry about the angle. We'll just get the magnitude of the current. So I don't have to worry about the star part. So we can just use this as if it were a DC equation. Solve that for I, and we're good to go. We got it. So we know that I equals S on V. Let's do that for both triangles. For the first triangle, this one, we got 196.8 kVA. Now, since this is in kVA, I'm going to put this in kV so they cancel out. So I'm going to divide that by 0.6 kV, and that cancels out, and I have amps left. Somebody tell me what we got for current. Dominic, you don't have no calculator?
Yeah, I'm doing it.
Okay. Why come you don't give me no answers? You putting all the work on Jacob. And Tresser, is your mic really broke?
I was doing what he was doing at first. I was trying to give everybody else a chance, but yeah, that didn't work out. But I got 328.
320?
8.
328. All right. So remember, 328 amps. Now let's figure out if with my power factor correction, we should be able to lower that. Let's see how much we lower it to. So now we got to take 171.8 kVA, divide that number by 0.6. So I got 178 divided by 0.6. What's my new current now?
286.3.
28. Let's just round it to 286. Okay. So that is now you might not think it's a big difference, but that's a huge difference. That's from 286 or 228 down to 286. Percentage wise, that's a lot of savings right there. So by increasing our power factor, decreasing the angle, we actually drop the current down. We're doing the same amount of work with less kinetic energy, because you get your kinetic energy from the current. That's the stuff that moves. Voltage doesn't move. Ohms doesn't move. The only thing that moves is current. So we're doing the same amount of work with less kinetic energy, with less stuff that's moving. That's pretty impressive. So I wish we had time to go more into this. This really, I mean, you can take a whole course in just this at UC. Just this topic right here. You can just take a whole 15-week course in that. I don't know. So this is it, though. We only have so much time in this course, so this is it. So anybody have any questions over? Really, we're done with AC power. We got AC power, power factor correction. Anything we've talked about that we need to go over, review? Any questions or comments on AC power? Well, if there's no questions, I don't know how to test you guys on this because you'll have everything right in front of you. We'll figure it out. I don't know. We'll figure something out. I keep saying that and the clock keeps ticking, but I'll have to figure it out. Well, I know Dominic and Jacob knows how to do it. I can just give them their A. But the rest of you, Sam and Tresser, maybe I'll test you guys and just give those two an A. Is that fair?
It's good. All right. See you later.
And you know what? I can tell Sam's not there. He didn't respond to that. He's probably sitting back somewhere, put his image up on the screen, so I think he's there.
That makes me wonder, like, what made you think of that the first time you thought, like, okay, they're not really sitting at the screen? When did that happen?
I was talking to my girlfriend because they do the same thing, and she told me she teaches high school, and she told me that they make their kids, they have to have their cameras on. I tried that, but Blackboard doesn't like that. I don't know if I tried that with you guys or not. I was at one class and it just crashed the whole system. Now, when I'm at the school, it's beautiful. We did that right before we went on this face-to-face thing. People were able to have their cameras open, and I felt more like I was in the class. I feel much better in front of the camera now, but boy, last semester was so awkward. I'm used to students and feedback and looking at people's faces. I can see when they have something and when they don't. But to answer your question, she told me that in high schools, they make the kids open their cameras up for that very reason, so that they won't, act like they're in class and they're somewhere out playing basketball or something like that. So, and then the other thing that made me think about it, though, because the only person that was participating was, I think, Jacob. But it says on my screen, I see Tresser, I see Jacob. Well, I guess we lost some people. I thought we had somebody call in. But the calling people are excused because they can't really interact. I guess they just listen to me. I don't know how it works. So I'm hoping that the people that are not participating are going back watching the lectures. The good part, last semester I put everything on YouTube, and I can go back and look at the number of people that viewed it. But I can't do that now because these files are so big, it takes forever to upload it. So I don't even do that. So I have no idea if you guys are going back, actually rerunning and watching these videos or not. But
So, one of the guys, he's doing co-op this semester, like unexpectedly, and I know that he told me he's been going in the classes that he missed. It's Randy. He's been going and watching them afterwards, even a couple times. So,
well, I tell you what, there's always something good. I think one thing, just us together as a group. When I say us, I mean the whole world. I had no idea I can do what I'm doing right now. I mean, I would never thought before this virus thing that I'd be standing in my basement teaching a class. I didn't even know. But sometimes you're forced into something, and then they have a saying. This guy Far Gray, he has a saying: "Comfort is the enemy of achievement." You get comfortable doing something you fail to achieve, but you got to go to area of discomfort, and then you can figure things out. So now that I know I'm able to do this, even when we go back face to face, I think I want a camera in the room, and I think I would like to record the lessons to give people the option. Well, I don't want it to be, it shouldn't be in place of coming to class, but I really do think that now I want to record every video and have it available for students. They can go back, they can watch it. I don't like these long ones like this, and I guess you guys probably saying, which I'm sure Dominic probably thinking, well, hell, if you didn't go off on so many tangents, the videos wouldn't be so long. But besides that, if we have a regular class that's an hour long or whatever, 50 minutes, like last semester was ideal. I can record it, put it up on YouTube, and people can watch it over and over again. So I think I'm going to always record these videos, even when we open back up. Now, they did ask me, the school called me 3 weeks ago when they were getting together classes for fall, and asked me if I wanted to go back face to face, and I said, I think I do. But now that I know more about this virus, I don't know how comfortable I am with that. So even if we go back face to face, I think I might, until we get things more figured out, I'm going to limit. We still probably going to do some, well, you guys will be done with me anyway, so, because I might do digital. He might give me digital. Every once in a while I'll teach electronics, but the guy that does it now, he doesn't want to get that class up. So I'm not even going to go there. So I don't know if I have you guys anymore. They tried to get me to switch back over to physics. The guy tried his best, but he had me in the physics department, and they didn't want to hire me full-time. And I begged and pleaded to hire me full-time 13 years ago. They didn't want to do it. He told me he couldn't do it. And then when the engineer, they didn't know I could do engineering courses too, because my degree is in applied physics, so I can do either or. And so I went and went to engineering. And then the guy was like, man, I didn't know then he tried to do everything to get me back to hire me full time, but it was too late then. He should have got me while he had me. But every once in a while I would do a physics course, and I have some of my old students. I get to see some of them. But I don't know now. All right, so assuming you guys got a chance to look at the video, tell me about it. What was going on in the video? What happened in the video? Did you guys watch it?
that was the bridge that got all wavy in the.
Yep. There was yep. You said the bridge got wavy, and what else? He was breaking up a little bit. The Tressor, is that Dominic? Oh, Dominic, you can just talk. You don't have to raise your hand. Really talk.
No, but yeah, I did just see the bridge. Well, at least I was thinking that maybe a relation that you were going to try to make was like something with sinusoidal waves, or however, I can't really pronounce it that well, but the way that the bridge was moving would just put me in that mind frame of like the sine waves that we had been looking at. And then apart from that, I just was wondering is this real? Like, is that a real video? Like, did that really happen?
Now a couple things I like what you said. First of all, did it really happen? It almost now remember that bridge is made of steel, and you saw it moving around like a wave. You saw it moving around, so it does look kind of fake, but it was real. But what I like that Dominic said, he said it kind of put you in the mind of a sine wave. If you go back, when you go back and look at that, look closely at the bridge. You see exactly what Dominic just said. You actually see a sine wave in the bridge. Let me talk to you about 3 different kinds of sine waves that exist. Here's one that exists. That's called a damped sine wave. Now remember, the height of this is the amplitude. So the amplitude is getting smaller, 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 smaller until it goes to 0. Now I know we've been talking about voltage and current sine waves, but think about energy now. Anytime something vibrates, think about something vibrating, like a string. You pluck a string. If I hit the board here, you can hear it because it's vibrating. And the board actually does this. It vibrates and it goes to 0 real fast. Anytime something vibrates, a vibration is like this. It moves back and forth, and eventually it slows down when it runs out of energy. You see what I did? It just went back and forth, and eventually it slows down. But if I have that back and forth motion like this, and I walk this way, look what happens. I get a sine wave. So if I take vibrational energy or motion and spread it out over time, here's what you get, a sine wave. So one kind of sine wave is one where you cause something to vibrate, and eventually it stops. Most things give you this kind of sine wave called a damped sine wave. So think about the kid in the swing. I got a kid in the, let me get a prop. You ever have a kid in the swing, you pull him up, you let him go, and it goes like this. And when it comes back, it doesn't go as high as before. Just eventually it stops. Well, that's this. It's doing this, and eventually the swing stops. But if I can walk like this, I'll get this damped sine wave. Because what happens is the energy that you give when you pull the swing back, you give it potential energy, and when you let it go, the potential turns into kinetic. It's fastest right here, then it goes back up, but never goes up as high as you lifted it over here because some of the energy gets dissipated as heat. There's friction at the connection point here, and there's friction because of the air resistance. And so that dissipates the energy until it stops. So anything that you cause to vibrate on its own eventually will stop vibrating because the energy dissipates. Then there's this one. And this just means it goes on like that. This is a forced sine wave. This would be like you pull the kid back in the swing, you let it go. Now you know when you let it go, it's not going to go up as high over here as you pulled it back because there's some energy missing. Energy dissipated from the air resistance, and then there's friction right here. But if you figured out how much energy you lose from air resistance and how much energy you use for friction where the swing ties to the actual pole up here, if you knew how much energy was missing and you replace that, this is what you get. You get a vibration that never stops. If you add it's like having a bucket of water with a hole in it. You figured out how much water is coming out. If you put water in as fast as it comes out, the level will stay the same. That's kind of what we're doing here. We're putting energy in as fast as we're losing it, so it'll stay the same. That's a forced sine wave. And then there's this one. That one. This one is called an over damped. Now you should put the word sine wave after each of these. You got a damped sine wave, a forced sine wave, and an overdamped sine wave. Now, if you saw the video, which one of those you think it was the bridge and why? It's one of the three. Which one?
Over.
Over is correct. Now, how do you go to an overdamped sine wave? How do you make an overdamped sine wave? Well, if I want to go from a damped sine wave to a force, what I do is I add energy, the exact amount of energy that's being lost, I add that amount of energy to it. So it's like the bucket thing again. If I have a bucket, and I got a hole in the bucket, and the water's coming out, if I add water to it at the same rate that it's coming out, then this bucket will stay, the water will stay level, the amplitude will stay level. But if I add more water faster, if I add water faster than it's coming out, the bucket's going to overflow. That's what happened here. So it's like doing this. If I take the kid in the swing and I bring it back, if I add the exact amount of energy that I'm losing, then he always comes back to the same height. That's this one. But if I add the energy, if I add more energy than what he's losing, every time he goes, he gets higher and higher and higher until I guess he'll go all the way around and you kill the kid. That's kind of bad to say, but at least in a cartoon you would, right? But you see what I'm saying? In order for that to happen, timing is of the essence. It's like this. I need a better prop. Hold on a second. Let's say this is my swing. The kid's in the swing, and he's swinging back and forth like this. I want to add energy to it. Does it matter when I push? And the answer is yes. If I push too late, let's say the swing comes up like that, and then it starts to come back down, and I push, I don't add as much energy. If I push too early, if I push while it's coming up, I don't add as much energy. If I push at exactly the right time, if I push and it comes up, for a second it's going to freeze. Before it changes direction, it stops. If I add energy at that point and I add more energy than what I'm losing, this is what I get. In that bridge, that whole thing started with a gust of wind. A gust of wind. The wind blew ever so slightly at just the right time. Everything vibrates, and the wind actually, a gust of wind, and everything has a frequency. Let me write that down. Everything has a natural frequency of oscillation. Everything has a natural frequency of oscillation. If I go to this, I pull it back, it moves back and forth at a certain frequency. The number of events per unit of time. It's determined by how I'm holding it. It's determined by the length of this. It's determined by several factors. But everything has a natural frequency of oscillation. If I hit the board and I hit this pipe, I hit the board, I hit the pipe, you can tell the difference between the two. You close your eyes, you can still tell because this vibrates at a different natural frequency than the board. What you're hearing is the vibration of the board, which causes the air to vibrate. Those vibrations go into your ear, which causes your eardrum to vibrate. Your brain picks that up as sound. So this vibrates and this vibrates, but it sounds differently because each thing vibrates at a different natural frequency of oscillation. The natural frequency is a vibration that you don't, once you get the thing vibrating, you step back and let it do its thing. So imagine having a guitar string that you pluck it, and when you pluck it, you let it just vibrate on its own. That's what we mean by natural frequency. That bridge in the picture, the whole bridge, had a natural frequency of oscillation determined by what it was made out of, how heavy it is, temperature, a whole bunch of things. It just so happened that, I guess the word is unlucky, they were unlucky enough to where the gust of wind exactly matched the natural frequency of oscillation of the bridge. And instead of giving it the vibration as time to dissipate, all those gusts of winds, the gust of wind kept adding energy to the bridge, making it vibrate more and more and more. This wasn't instantaneous, guys. You go back and look at that video. Now you got to remember, I think it was the 1940s, if I'm not mistaken. There were no cell phones. There weren't even, I mean, TV was new. So they had to have enough time. I mean, just look at the cars in the picture, how old school those cars were. These people had to have enough time to watch the thing vibrate, go get a camera system. They didn't just whip it out of their pocket like you do on your cell phone. They had to go get a camera, set up, and film that. This went on for some time. You can look up how long it took to collapse. But this thing went on for some time, this vibrating back and forth. So eventually, in this overdamped situation, it tore apart steel and concrete. And even when the main part of the bridge fell, the thing was still moving in a sound wave as if that part was still there. So go back and look at that video again with fresh eyes, and you'll see what I'm saying. Dominic was the one that brought it up. It made him think about a wave. But Dominic, I don't know if you know that even when the span of the bridge fell, the part that was missing, it still moved as if that part was still there in a sine wave, because what you had is an overdamped situation. You can actually see this in the bridge itself, the actual sine wave. So here's the point. Everything has a natural frequency of oscillation. Everything in the universe has a natural frequency of oscillation. And so they have a name for that natural frequency. I'm going to give it to you right now. The natural frequency of oscillation is called the resonant frequency. The resonant frequency. And when something is moving at its natural frequency, let's say you take a guitar string and you pluck it and you step back and let it vibrate, that frequency is called I can't spell today. I think that's right. Resonance. I think I spelled it right.
You had the N in the right spot before, right? Resonance?
Resonance. Is there two N's in there? I don't know.
Somebody better Google that.
I'm not embarrassed because I'm not putting this on YouTube because I don't know who watches it on YouTube. But,
Yeah, that should be right. Resonance.
So you took phonics when you were.
You're right the first time.
So this is it. I think that's resonance. It's like the word dance, so resonance. So I think that's right.
Yeah, that's right. As long as that's yes.
Yeah, that's a sun. Yeah, resonance. All right. So you should be wondering, okay, how does that apply to electrical circuits? Do electrical circuits have a resonant frequency? And the answer is everything has a natural frequency. So let me show you some. Let's say I take a battery. And a capacitor. And I hook it up. What's going to happen when I hook it up? Now, this is a DC, not an AC circuit. If I hook it up, that capacitor is going to charge up. So it's going to charge up to a certain amount of voltage. And remember, even though capacitors store charge, they really store energy. So I charge that capacitor up, and then when I disconnect it, I have energy stored in that capacitor. Now, say I have ideal devices. If I have ideal devices, that means I don't have any resistance at all. In the real world, we always have resistance, but on the board, we got ideal devices. I charge the capacitor up since there's no, it takes 5 time constants for it to charge, but since there's no resistance, it charges right away. After I charge it, I do this. I hook up a switch to it. And I got that inductor. I close the switch. What's going to happen? Well, what's going to happen is when I close that switch, the capacitor is going to discharge. So it's going to discharge, sending current that way. When current flows through an inductor, it builds up a magnetic field around the inductor. The cause of the magnetic field, if you remember from DC, is the current flow. The cause of all magnetic fields is current flow. So as long as there's current flowing, there's a magnetic field around that inductor. And I have energy stored in that magnetic field. The energy came from the current from the capacitor. As soon as this discharges, no more current in the circuit. There's no current to sustain the magnetic field. So guess what it does? It collapses. Well, Faraday says if we have a coil, if we have a magnetic field, if there's movement, I'm going to induce a voltage across the inductor, which could cause current to flow. So as this field is collapsing, I have Faraday's law going on. So I have a current forced back into the capacitor. Guess what happens now? As long as that field is collapsing, it sends a current to the capacitor, it charges the capacitor up. And then guess what happens? It keeps doing that over and over again. The current flows back and forth, back and forth, back and forth. Anytime you have a back and forth movement, that is what we mean by a resonant frequency, the resonant frequency of oscillation. Well, you might say, all right, well, okay, what good is that? Well, we'll get to that in a minute. Don't worry about that. Let's look more into this stuff. This gets real interesting. And guys, interrupt me at any time if you have questions. This I can talk about for hours. I won't. I'll bore you. I will not bore you. Plus, I got this thing set to time out soon. So we'll just start this and we'll come back to it. At least I'll at least get to the theory part of it. So think about this. Go ahead, Sam. Sam, you can just interrupt. I can't see that hand when you raise it. Go ahead and ask.
I just wanted to interject since you said that this thing might be auto timing off. For lab 2 and 3, Blackboard was messing up on me, so I sent it to you via email.
Okay. All right. Let me. I think you sent me something along those lines. Okay. I'll check that out. When did you email it? Did you email it when it was due, or did you email it after it was due?
I emailed it before it was due because I submitted it from Blackboard, and then I went back to take a look at it, and none of the pictures were showing up. So I sent the Word document to you via email as well.
Okay, I'll check it out. All right. Imagine I had, well, you don't imagine anything. This is real right here, right? These equations. Look at the circuit, though. Let me give you a circuit for this. All right. Now, my generator, I'll do this. Now, you know in DC when I do that, that means I have a variable voltage source. All I can vary here is the voltage. In AC, I can vary voltage or frequency. So I'm gonna put an F right there because we're not varying the voltage. I have a knob there I can change the frequency. And the question I want to ask is, what happens to XL and XC and the current and all of that in the circuit as I change the frequency? What happens? And I want to start by say, all right, we got this set at 0, right? Well, what happens when I set that to 0? What's the value of XL, XC? Well, XC, if this is 0, if this is 0, then this right here, I have 1 over 0, right? Which is infinite. That means I have a really high resistance, opposition, infinite. The capacitor reactance value, ohms, is really, really high. It's infinite. And here, I put a 0 in for this. This is 0. So if I start my frequency at 0, let's make a graph. Let's do a graph. You see, as I turn this up, as I turn the frequency up, this, because F goes up, this value is going to go up. And as I turn this up, since they're indirectly related, this value is going to go down. So you can see that from the equation. I want to erase this. And let me go back and ask the same question, but this time I'm going to use a graph. So on here I have reactance. And right here, I got frequency. And I got this set to 0. Well, we said that 1 XC is 1 over 0. So XC is like right here. It's really at infinity, but I can't draw this high enough for that. So we'll just start at really high. And if this is 0, then XL is at 0. So it's like right here. XL is right there. So if you look at the equations again, XC is 1 over 2 pi FC, and XL is 2 pi FL. As I increase this, this goes down. And as I increase this, this goes up. So as I turn the frequency higher and higher, look at what this is. XL is going up. At the same time it's going up, XC is going down. You can see that just from the equations. If I increase the frequency, XC is going to go down. If I increase the frequency, XL is going to go up as I sweep my knob across my frequencies. So just looking on the reactive axis, this part right here is moving that way, XC, and XL is moving this way. Well, at some point, guess what's going to happen? At some point, they're going to be equal. XC equals XL, and that's that point right there. But remember that this right here has an angle associated of 90 degrees, and this has an angle of minus 90 degrees. Or remember that this has a plus J operator and this has a minus J operator. So let's just say this reaches 100 ohms. At this point right here, this is 100 ohms also, but one is positive, one is negative. So guess what happens right here? Right, they cancel out. So at this frequency, at the frequency where this happens, we call that the resonant frequency. That's an F with an R subscripted. The resonant frequency is the frequency in the circuit where the reactive, capacitive reactance, and the inductive reactance have the same magnitude. But since they have the opposite phase, they cancel out. So if they cancel out, let's say everything was 100 ohms. You'll understand this. No, let's say it was 1,000. Let's say that this was 1,000 ohms. At this point, this was 1,000 ohms, and this was 1,000 ohms. So you see, you got a lot of ohms in this circuit. At resonance, these two are equal like they are right now, but one of them has a positive J operator and the other has a negative J operator in front of it. So everything in this box right here has the same magnitude but opposite phase angle. So guess what happens? They cancel out. And the only ohms that exist in the circuit are the resistive ohms. Let's think about current. What happens to the current? Well, you can see from here, if I went from having all of these ohms in there down to just that, if I decrease the ohms, the current's going to go up. If I take this opposition and that opposition out of the circuit, the lower opposition means I have a higher current. So current-wise, as I approach the resonant frequency, the current's going to go up. Now, think about over here. If I start right here, I still got a lot of ohms in the circuit. Most of my ohms come from the capacitor. As I move this way, they're decreasing. At this point, these two right here cancel out, and the only ohms I have in there is the resistor. If I keep going past the resonant frequency, I have more ohms now, this time coming from the inductor. The only place in here, the only sweet spot I have, where I have the least amount of opposition, is at resonance. Because at resonance, the two reactive components equal each other in magnitude, but they have opposite phases, so they cancel out. So you would expect the current to peak at that resonance, and that's exactly what happens. Let me draw the current curve for you. Again, I don't want to erase my pretty picture. Damn it. I just have to erase it. I'll do it down here. All right, so here's what happens to the current. Right in the middle, we always just grab it. Can you guys see this down here? Can you see it, Jacob, Dominique, Sam? Can y'all see this down here?
Yeah.
Okay, so this is the, what you draw this. I thought I had, let me see which one of these is the darkest. I think that one's better. All right. You draw the resonant frequency in the middle. Now, when I'm over here on this side of resonance, I got a lot of ohms from XC, so I don't have a lot of current in the circuit, because the current in the circuit is going to equal the voltage divided by X divided by R plus XL plus XC. Well, right now, where I am, because I'm at zero frequency, 0 hertz, XC is really, really, really big. So this is really big. So I'm still dividing by a large number of ohms. They just happen to come from the inductor. So that means my current is going to be really small. So I'll start out over here. As I walk this way, I'm getting closer and closer to this point, the point to where XC and XL equal each other. So they're starting to cancel each other out more and more. As this shrinks down and this grows, eventually they're going to be the same size, but one's going to be positive, one's going to be negative. And when I hit that point, these two right here are completely gone. And the only opposition I have is that, which means my current's going to be really high. So as I approach this point, here's what happens to the current. And right here happens when I'm right there. That right there is the maximum current. you get maximum current. When these cancel out, so the only opposition is resistance. So I get I max equals V over R, because these two cancel out at resonance. If I go past resonance, now I'm introducing XC again, but look at what happens to XL. XL now is getting bigger. And so I'm starting adding more ohms from XL, so my current is going to drop off like this. And that's called the resonant curve. Let me put that over here. See it? Now, this is kind of interesting if you think about it. Because, well, let me put it like this. What would the power be right here? The power right there. That's P max. Can you see that? That's P max. If I use maximum current to count, now I erase the circuit, so I can't point to the circuit. If I use the maximum current in the circuit, it's going to give me the maximum power of the circuit. So I can calculate P max by taking I max, squaring it, and multiplying by R. That gives me the power right there. See it? Now, let's say that on that circuit I erased, I wish I had it up there down, I had a ammeter in there so I can measure the current, so I can see what I max is. There's a point here that's important. One point is the max current. You can get that by using this equation. Whatever circuit I give, you take the resistance divided by, take the voltage divided by the resistance. That gives you the maximum current, because remember, these two, XC and XL, they're not there at resonance. So if I'm at resonance, I have the maximum current flowing, and there's always just V over R. Once you get that value, you can take 0.707 of it. If you take 0.707 of it, it's going to give you a point right here. This right here is 0.707 I max. Okay, so just, it's not hard, just follow what I'm doing. Listen to what I'm saying. If you knew what I max was, let's say I max was 10 amps. Let's say that was 10 amps. Where did I get that number from? I don't know. Let's say I got the circuit, I give you an ammeter, you measured it in lab. You measured it to be 10 amps. If you know that's 10 amps, if you take 0.707 of, you get, right there would be 7.07 amps. You multiply that by 0.707, you get 7.07 amps. So no matter what value you get for I max, when you multiply it by 0.707, you'll always get a point less than I max, because you're multiplying by 0.707. So if this was 10 amps, that'll be 0.707 amps. If that was 1 amp, that would be 0.707 amps, and so forth. Now you might say, okay, well, why is that important, that point right there? Well, what would the current be right here at that point? How would you find the current at that point right there? What would you do? Anybody know how to find the current there? How would I find the current at that point? How did I find the current at this point? What did I do? How did I get that I max? What did I do?
Over R.
Nope, not B over R. It's right here. Oh, yeah, you're right. I'm sorry. Who was that, Dominic?
Yeah.
I meant the power. How did I find the power at that point? When I said
Okay.
no, power. How did I find the What did I do to get P max? It's right here. I took the maximum current. I did what? I squared it. I used Watt's law. I took the current times resistance. I do the same thing here to get the current. So what is the current at this point right here? What is the current at that point? What is it? How much is it? What's the current at this point? Isn't it I max? The current at this point is I max. So what is the current at that point?
0.707 IMAX.
Yes, that's the current right here. So Watt's law says if I take the current and I square it and I multiply it times the resistance, what I get is power. Well, here's the current. So if I take the current and substitute for I, here's what I get. I is 0.707 times I max. I got to take that and square it and multiply it by R. If I do that, I get the current at this point. You guys agree with that? If I take the current, I squared times R, I get the current right here. Now, remember in your math class, they told you in your math class that you have the product of two numbers raised to a power, then that's equal to each individual factor raised to that same power, right? So you can apply that right here. If I have 0.707 times I max squared, that's equal to 0.707 squared times I max squared. Can somebody take 0.707 and square it for me? Let me know what you get.
It's like 0.499. So what? What do you want? 0.5?
Okay, so it's 0.5, right? It's 0.5. So all this right here, that right there, is 0.5. That's what Jacob just said. He said this right here was 0.5, right? So I can rewrite this another way. I have P equals 0.707 squared times I max squared times R. And Jacob just told me that this right here evaluates to 0.5. So I can erase that if I want to and put a 0.5 there, right? So that's the power at that point. That's the power at that point, because that's what I asked you for. But anybody recognize this right here? What's that right there in the circle? I erased it, but you have it on your paper if you're taking notes. What is that right there?
P max.
P max. In other words, let me get rid of this. In other words, the graph looked like this. And you did this. We started out like this. And I asked you for the current here. Well, that's resonant frequency. So at resonant frequency, the reactive components are equal, so they cancel out. So to get the current there is easy, because the only opposition in the circuit is the resistance. So that must be a maximum current. So you know right there was I max. And then I said, okay, well, if you know that's I max, how would you get the power there? Well, to get the power, that's easy. You just take P is I squared times R. But since I'm using the maximum current to get that power, that's going to be the maximum power in the circuit, P max. And then for no apparent reason, I say, all right, let's take I max, multiply by 0.707, and let's get the current right here. How would you calculate that current? Well, you said take 0.707 times I max, and that gives me the current right there. And then I said, okay, well, how would you find the power there? You said, well, you do it just like here. You take P equals I squared times R, but in this case, this is I right here. So I got to take 0.707 squared times I max squared times R. And now Dominique is saying, all right, well, if I look at this, that's just P max. So I have 0.5. Well, 0.5 is like 1/2. So what I really have is 1/2 P max. 1/2 P max. So if the maximum power was 100 and I go down to this point, it's going to be 1/2 of that, 50. If the maximum power was 25 watts, when I go down to here, it's going to be half of that, 12.5. Guess what they call this point? Just guess. The half power point. So this point right here is important. That's PHP, and that stands for half power, the half power point. And whatever the maximum power is, the power right there is always half of it. So if I tell you at the circuit you got 100 watts, down here, we're just getting started, guys. You're going to love this stuff. This is going to explain so much, and it's 4:11. I feel myself having to stop, and I just really want to keep going. But this explains the world. When I learned this made my electrical world. It just blew my electrical mind. So we're just getting started. You just wait. Unfortunately, we got to finish this next time, but let me just finish this up. This is the half power point. Now, let's say we drew a perpendicular line. I don't have enough colors. I'm going to draw a perpendicular line through the half power point, like this. I'm going to intersect the curve on this side and this side. And then I'm going to drop a perpendicular down on both sides of FR. So one here and one here. And I'm going to call this F1, F2. F1 and F2. What I've just defined now, we only dealt with one frequency, the resonant frequency. But now I can go down to F1, up to F2, and I've defined a whole range of frequencies in between here like this. A whole range, a whole band of frequencies. So guess what they call that band of frequencies? The band, you ever heard of bandwidth? Oh yeah, you've heard of bandwidth. If you deal with a computer, if you deal with a cell phone, if you deal with any kind of device that communicates, you heard of bandwidth, but until now, you didn't even know what they were talking about. What you're going to know after we get done with this. The bandwidth, the amount of room between from resonant to the lower, these are called corner frequencies. It's in a corner, right? This is a corner frequency. That's a corner frequency. They're also called the break frequencies, or the 3 dB. They have a lot of names, but they define bandwidth. Mathematically, bandwidth is defined F2 minus F1, and it's exactly what you think. The bandwidth is the amount of room, electrical room we have to do something. And there's something we're going to do, we got to talk about that. But the more of this I have, the more area I have to do stuff when we get to the stuff that needs to be done. like 6 minutes, so let me just, where can I stop here? I'm trying to think of a good place to stop. I hate this. All right, I guess I'm gonna have to stop here. There's one more thing I want to. All right, I guess I'll stop here because I don't know. I don't want to. All right, let's just review what we got so far, and I'm about to keep up with this story on the next video, on the next lecture. So here's what we got so far. You know what we could do? Let me derive this for you real quick. I think I can derive something for you. Look at this, and we'll pull it all together. So real quick, on that other graph, remember the other graph was like this? This was frequency. This was reactance. And on my circuit, we start the frequency at 0. So at 0, XC was up here, and XL was like right there. And then I started to increase the frequency. Well, as I increased the frequency, XL was going up like that. At the same time, XC is going down like that. So as this is moving down that way, XL is moving up that way. And at this point right here, at that point right there, that's where XC is equal to XL. But because one has a positive J operator and one has a negative, they're going to cancel out. And the only opposition you have in the circuit is resistance, and that's what causes the current to peak to give you I max. The frequency at which that happens is called the resonant frequency. So, if I go back to my original problem where I have the capacitor and the inductor, I charge this up. The current's going to move back and forth at that frequency right there. The question is, can I calculate that frequency? How do I get to the frequency? Well, the answer is right there. It's the frequency at which XC and XL are the same. We know how to get XC. We know how to get XL. All we got to do is set them things equal to each other, and we're good to go. So I got 4:16 on my clock. Let's do that real quick, and then this will be what we pick up next time. I want to know, how do I calculate the resonant frequency? So, it's this. XC is the same as XL. I know XC is 1 over 2 pi FC. I know that XL is 2 pi FL. So I just got to start doing some math here. So help me do the math. Well, let's see. I guess what I want to do is, let's start on this side. I want F by itself. So that means I got to divide both sides by 2 pi L. Divide this side by 2 pi L. And then these will cancel out. This will cancel, that'll cancel, that'll cancel. And over here on the right, all I got is F. Okay, well, I guess that works out. So this will cancel out, and all I have is F. And then over here, well, I got a mess over here, don't I? Not really. I got 2 times 2, which is a 4. I got pi times pi, which is pi squared. I got FC over 1 equal to F. So let me put that up there. Let me put it over here. I have F equals 1 over 4 pi squared FC. We're almost there. All I got to do is get rid of that F. Right there. How do I do that? Well, I multiply both sides by F. I multiply this side by F, and multiply this side by F, and these F's are going to cancel out. And then what I'm left with is, on the left, F times F is F squared. And on the right, I got 1 over 4 pi squared. I forgot my L. 4 pi squared LC. I should have an L here and an L there. I forgot the L right here. It's right there. So I'll erase that one. I got the L right there. That's where that L came from. So I'm almost there. I just got to take the square root of that, and I'm good to go. Then we can stop. So I take the square root of both sides. And if I do that, the square root of F squared is just F. That's FR, this is the resonant frequency. The square root of 1 is just 1. The square root of 4 is 2. The square root of pi squared is pi. And the square root of LC, well, I can't do that, so I got to keep the radical sign there. So now I have a formula that I can actually use to calculate the resonant frequency. You give me that circuit again that I erased. You tell me how many volts that you're putting across the circuit. I can tell you the maximum current. I can tell you the maximum power. I can tell you the power at the 3 dB point. The maximum power. I can tell you at the half power point, and I can tell you the frequency at which that oscillation is going to take place. If you give me the value of L and C, I can put it into here, and we can calculate the resonant frequency. Now, what you don't know is what we can do with this. That's why you're not as excited as I am. But when you find out, then you'll be excited too, because this explains the whole electrical world right here, right here. So I'm gonna have to stop here. I'm already 1 minute over, and I don't want to steal any time from you, because then you'll throw that up in my face later on. Remember when I gave you extra minutes in the lecture? So I don't want you guys to have that kind of influence over me. So I'm going to stop right here. And today is Monday. On Wednesday, we will pick up with this. We got a lot more to talk about. So we're talking about resonant circuits. I don't like the way your book does it. I hate the way he does resonance, but if you want to read about it, he splits it up, and it's just kind of weird. You can read about it if you want to, or you can go to YouTube, look it up, or you can just wait for us to come back in 2 days. Anybody have any questions or comments over what we talked about so far? I know it's a lot, but it'll make sense.
I've got a question kind of about this, kind of about everything.
Okay. I like questions about everything. Go ahead.
Yeah, so we have a recurring theme with multiplying things by 0.707. So we find the RMS with that, and then use it for this half power point as well. What's the significance of that?
I can't answer that. I think it's a calculus thing. But one thing you said, don't think about when we're doing this. I know 0.707 times the peak value is RMS, but when we're doing this, don't think that. This is not that. So what he's saying is this number keeps coming up to 0.707. It comes up for RMS. I know it means a root mean squared for RMS, and that has to do with heating effects, but I'm not really sure, and I've actually thought about that for a long time. I just never had a chance to research that and look it up. My guess is it's more of a calculus thing, but I don't know. That's a good question. Really good question. And I'm not going to be able. You guys can dig into that if you want. Let me know, but I won't have time to research it. So sorry, I don't know the answer to that, Jacob. But it's something I thought about a lot.
That's okay. Honestly, I'm probably gonna have a look because I'm pretty curious. I don't think it's coincidental that it pops up again.
No, it's not, and it pops up in other places. So no, it's not a coincidence. It's not. Anybody else have any more questions? Okay, well, if you do find something out, Jacob, let me know, or let us know what you research. And guys, if you don't have any questions, remember that if you have my number, send me a text for attendance. I see some people have already signed off, but text me at that number. The class number you should know by now is EET 132. Just send me a text for your attendance, and if there's no more questions, then I will see you guys on Wednesday. Have a great rest of the day.
I got one more thing. You can turn the recording off, but I sent you a text yesterday asking a question about the homework. Just ignore it. I figured it out pretty quick. I hadn't read all the way through yet, so I figured it out by